All right, last time we talked about Bayes' theorem quite a lot and also introduced random variables. And today we're going to talk about expected value. Which is a very important measure for understanding random variables and distributions. So let's get started, and let's first give a little context for the next 2 days. We're actually going to talk about two very useful measures. For understanding random variables. For understanding random variables and distributions, you will remember that a random variable gives you a distribution, so the two are very closely related. And these two things we're going to talk about are the expected value, also known as the mean, and the variance, and closely related standard deviation. And what these two things mean, we'll talk about them a lot and you'll understand them in a lot more detail. But just to introduce it, the expected value is some kind of center of the distribution or random variable. So if you think about it in terms of these graphs that we were drawing, it would be essentially in the center of the distribution. Although we'll see some examples, it does not mean that it is the highest point necessarily. It's slightly different from that. Maybe I'll draw it like that, just a bit off of the highest point, to emphasize that essentially means the center, but it's different from being the most common outcome. And then variance and standard deviation, how do we understand these things? These are a measure of the spread of the distribution. So if we have some picture of a distribution like this, then they are measuring how spread out is the distribution. So today we are going to focus on expected value, and next time we will focus mostly on variance. So let's get the definition. The expected value, or mean, of a random variable let's say a random variable on a sample space S. So we denote the expected value by E of X, and it is defined to be the sum over all elements of the sample space, probability of that outcome times the value of the random variable at that outcome. So essentially, we are taking a sort of weighted average of all the possible outcomes, where we're averaging the value that the random variable gives weighted by the probability. So let me write that down. It's sort of a weighted average of outcomes. And that's some kind of way of saying that it's measuring the center, or the way we're saying now, the average of this distribution. So let's do a little example. So for example, x, the random variable, which is rolling a 6-sided die, what is the expected value of this? So intuitively, we expect it to be, like we were saying, the center of the distribution. So when we're rolling a 6-sided die, what is the sort of average result we can get? Well, the results are the numbers 1 through 6, and the average of those is 3.5. And that's essentially exactly what we're going to do to find the expectation. So in this case, S is equal to the numbers 1 through 6 with the uniform distribution. And our random variable is not adding too much to the picture. It is just sending S to itself. So expected value, which is the sum. So it's the sum over elements of the sample space. So in this case, let's write that as sum from k equals 1 to 6. And then what is the summand? It's the probability of k times x of k, but that's just k itself. And what are these probabilities? Since we have a uniform distribution, they're all just 1/6. So when we write out this sum sort of in long form, what we get is 1/6 times 1 plus 1/6 times 2 up to 1/6 times 6. And you can see that essentially this is, in this case, literally just taking the average of all these values. And what we get is 3.5, exactly as we would expect. So already in this example, note the expected value is not the most common outcome. For example, in this example that we just did, it is not even a valid outcome at all. So if you roll a 6-sided die, you will never roll 3.5. So the expected value doesn't have to be an outcome. It certainly doesn't have to be the most common outcome. But like we said, it is a sort of weighted average. So it's telling you where your distribution is centered, but it's not telling you anything about individual outcomes. And let me maybe write this as a general rule. This generalizing this example for uniform distributions or uniform random variables. So if x is uniformly distributed on the set 1 through n. So remember, if we have a random variable, then looking at the image of this random variable as a function to r, together with the probability that x takes each of those values, which we defined last time, gives us a distribution. So when I say things like this, what I mean is that distribution that results from this random variable is the uniform distribution on this set. So if x is uniformly distributed on the numbers 1 through n, then the expectation of x, or the expected value, you can basically see from the definition, with a little bit of rewriting, is just going to be the average 1 through n over n, which is n plus 1 over 2.